In this video, we're going to be working with cycloids and creating parametric equations to model their path. So let's take a look at this example. So we have a circle here on a horizontal line. So let's say we are trying to find a point, trying to model the point A and its movement. So our first step is going to be to replicate this circle, and we're going to say that this is the circle at time equals 0, and this is it frozen at time equals t. So we know the radius and we know how fast it's going. So we're going to approximately draw a cycloid, and we're going to say the point that of our interest is right around here. So we know that's going to look something like this. So now this is the angle turned, and since we're moving 3 radians per second, this angle is going to be 3t, or we can just call it theta, but we'll call it 3t. So we'll label this point P, A, B, and C. So we're going to, if you remember unit circles, P can be represented as x of t and y of t. So we're going to say that, so we're going to also draw in our origin. We're also going to draw in our origin. We're going to say it's right here. But that's only for reference. So we know that OP, so origin to our point of interest, is equal to OA, which will be this vector. We're taking a vector tree approach, plus AB, that vector, plus BC. So essentially breaking it down into components that are easier to solve, plus CP. So we know the coordinates of A, so that gives us our OA vector. So technically the origin should be on this line, but just for convenience sake, we're going to put it off to the side. So now AB. Well, what is this vector? Well, we know that this arc length is equal to the radius times the angle. But we also know that this length is essentially this arc length in terms of length. So we know that this is going to be equal to our angle times our radius, which in this case is going to be 6t. So we are going to be moving negative 6t and no change in our y. Now let's look at our BC value. So since it's the point of tangency, this is perpendicular, forming a 90-degree angle. Therefore, we're going to be moving nowhere in the x direction, only in y. So it'll be 0, positive 2, since we're going 2 units up. And now CP. This one's a bit harder, but it's pretty straightforward. So we know our radius length is 2. That's the magnitude of the vector. Now what we don't know is the angle rotated. So we're going to put cosine, we're not exactly sure right now. So we know that this, if we're trying to be oriented in the BC direction, that's going to be a radius, that's going to be an orientation of pi over 2 from that line right there. So in order to look here, we're going to want to subtract pi, bringing us looking at B, and then add 3t. So in other words, we're going to be negative pi over 2. So like from here down to looking at B, and then we're going to add 3t. So that we are looking at P. And then we mimic this, but instead of cosine, we add sine for the y. So in this situation, our x of t, so our pair of parametric equations, is going to be 8 minus 6t plus 2 cosine negative pi over 2 plus 3t. And then for y, we're just going to sum the y components. So that will be 2 plus 2 sine negative pi over 2 plus 3t. And this will model the movement of A to P. Alright, this problem is going to be a little bit harder, but it's essentially the same principle. So we're first going to start off by making our second circle. So frozen at time equals time t. You can just pretend those are equal. Same circle. So we already know this piece of information, and this is all we need. So we're going to say roughly the cycloid looks something like that. So we're going to say it's here. This is our point of interest. So we're again going to draw our radii. So this will be 4. And since we're going 2 radians per second, in t time units, we're going to have rotated 2t. So now we're going to set up our vector trip. So we're just going to label the points P, B, C. So we're going to find that OP, so we're just going to draw on our origin right here. So we're going to say OP is equal to OA plus AB plus BC plus CP. So the exact same trip. So we know. So now we're looking at AB. Well, we need to figure out its length. So we know that this arc length is equal to distance. The distance of the arc length is equal to the theta value, so 2t, times our radius, which is 4. So this is going to be 8t. So there we go. That's our length traveled. So we know it's going to be equal to 8t cosine. But what is the angle that it's going up? Well, we have the slope for our line. So how will we use that? So let's say let theta of line, so we'll just say theta L, equal inverse tan, because tangent gives you slope of 1/3. So think about that. Since we're going this direction, tangent function can give you any of these values on this side of the unit circle. If you think of this as the unit circle. So we can just use this function to determine our angle. So we're just going to put theta of L here. And then same, but we're going to use sine this time. So now we're going to look at BC. So we know that our magnitude of the length is 4, because it's the radius. So 4 cosine. But what we know it's perpendicular to this line, but that line isn't horizontal. So we need to take our previous angle, so our theta L, we're going to add pi over 2, because we're going to rotate 90 degrees from our previous angle. And then same situation for the y, but we're going to use sine. And then now we're left with our CP. So we know our magnitude is 4 cosine once again. So we need to put our previous angle first. So we're gonna have our angle as if we were looking from B to C. So we're gonna put that one first. So our theta L plus pi over 2. Now what do we need to do so that we're looking at P? Well, I propose that if we simply subtract pi, which would have us be, if we're at C, looking at B, and then subtract 2t, we're going to be looking at P. So we're going to subtract pi from our angle, and then subtract another 2t, and that will give us that we're looking at the P direction. So this entire thing is the angle. And then same situation, but we're going to replace it with sine. So x of t is is equal to, we'll just say sum of our x components, so we don't make a mistake. But of course, check with your teacher to see if you need to write it out. And sum of y. And this would model A moving to P. Similar situation, except this time we're in the bottom part of the line. Well, this time we're asked to model the function of f, model its parametric equation. Well, we've only done it when we've modeled for A, so what will we do here? It's actually pretty simple. So first we're going to model the path of A, and we'll see how we can modify that to model the path of f. So our first step is to make our circle. That's going to be frozen at time t. So let's roughly say it's about here. We'll say it's there. So we're going to move it like that. So this is a 90-degree angle. That's our center. And this is our point of interest. That's P. And we're just going to put this for now, P star, but we'll get back to that later. So we have our A, our B, and our C. And we'll put our origin right there. So same situation. We're going to create our vectors. So OA plus AB plus BC plus CP. So we're going to say OP is equal to the sum of those vectors. Plus BC plus CP. So we know our OA because that we were given its coordinates at 2, -3. We're given AB. Well, we're not given it, but we know how to find it. So we know that this is going to be t because we're only rotating 1 radian per second. So we're going to have we also know the radius. So since these two are equal, we multiply the angle times the radius, and we get that this is 3t. So that's the magnitude. So 3t cosine. And now we need to find our angle again. So we're moving in that direction. So we're just going to set up our let theta L equal inverse tan of -2/3. And since we're moving to the right, we don't need to add or subtract pi. We'll get to an example where we will have to do that later. So 3t sine theta L. So now we're going to look at BC. So last time we added pi over 2 because we were looking up. But now we're going down. So we're actually have to subtract pi over 2. Because think about it, if we're moving this way and we want to subtract pi over 2, that would make us look at C. It's all about reorientating yourself so that you're looking in the right direction. And we're doing this in radians. So now our CP value. So we're going to take our magnitude, which is 3, and we're going to have our previous angle, which is theta L minus pi over 2. So now we're looking this way. So what we're going to do is we're going to add pi and then add t so that we look at P. And hopefully that makes sense. So this models our trip for A, but we were asked to find the trip for F. So I propose that if we were to keep OA, AB, BC, CP, and obviously x of t and y of t is equal to the sum of the x components, sum of y components, if we were to simply get rid of this pi, I say we're now looking at P star, which would be the path of F. Because think of it, F is halfway through its cycloid trip. because a cycloid looks like that, right? So point F is here, while point A is there. So therefore it makes sense that if point A is on one side, it would have to be at the exact opposite side. So that's why we can just take away the pi, or if we have a negative pi, we can add a pi. And now this would build a parametric equation that models path for F. Now how about you try this one? Alright, so now our first step is going to be to create our second circle. Make it a little bit larger. Okay, so that's our second circle. So we know that the path is roughly going to be like this. So we're going to say it's there. So we're going to say that that is our point of interest. So we'll call it P. So this is going to be C, that's going to be B, make our origin there, and we'll create our vectors. So we're basically breaking down a complex situation into simple ones that we can handle. So OP, we're going to set that equal to OA plus AB plus BC plus CP. So now we know our OA because we have its coordinates, which is negative 4, 1. Now we have to find AB. So we know that this angle is going to be 4t because we're moving 4 radians in 1 second in 1 time unit, and since we're going frozen at time t, say 4 times t. And since we know our radius, we can find the arc length, and it'll have the same magnitude as the distance covered, although it's not drawn to scale. This will be 12t. So AB is going to be equal to 12t cosine. Now in the previous time we had been moving right, now we're moving left. So if we let theta L equal to inverse tan of negative 1/4, which would seem like the right thing to do, that would be making us move to the right, but we want to move to the left, so we're actually going to add pi to that. So think about it now, we're going to be on the exact diametrically opposed to what we're looking at, which follows what we're looking at here. So 12t cosine theta L, so theta L encompasses the inverse tan plus pi, and 12t sine theta L. Now let's look at BC. So we have its magnitude, 3, nice and simple, so cosine. So we're going to have our previous angle, theta L, and we're going to subtract pi over 2 since we're underneath the line. And same situation, but for sine. And now CP. So we're going to want to take our magnitude, and we're going to have our previous angle, which will be theta L minus pi over 2. And then we are going to, since we're now looking that way, we're going to subtract pi and then subtract 4t. So that will allow us to be looking at P. And then same situation, but sine this time, because it's the y. And then x of t would be the sum of the x components, y of t would be the sum of y components. So like negative 4 plus 12t cosine, etc. Now let's say we wanted to find the diametrically opposed point. Do you know what to do? It'd be very simple. So we would just add pi to this, making it null, and then over here too. And now this would graph the cycloid of the point right there. So we'll call this P initial. So that would graph the cycloid of P initial, just changing that one little thing at the end. Hopefully that makes sense. All right, let's do this one. welcome to pause the video and try it on your own, but this one appears a little different, but we're going to tackle it the same way. So our first step is going to create our second circle. Alright, great. So these are supposed to be the same size, just so you know, it's the same circle. So we're going to say the cycloid looks something like that, right? So it's there. That's 90-degree angle. This is 4, that's 4. So we're not going to look at F right now, we're just going to model A first, and then we'll see how we can modify our equation to get F. So since we know we're moving 2 radians per second, we know this is going to be 2t. And if it said 2 pi radians, it'd be 2 pi t. So it's just taking that number and multiplying it by t. And then now we know that these two lengths are going to be 8t, because 2t times 4 is 8t. And since they're equal, they both work. So we're going to label our points, P, C, B. We're going to have our origin. Say OA plus AB plus BC plus CP. Let's work that out, just so we have our axiom. Oops. So we'll write that out just so we have our axiom. OA plus AB plus BC plus CP. Alright, great. So we're going to have our OA, and that's going to be equal to our magnitude, which is 8t, cosine. So we're going to create our let theta L, and since we're moving right this time, we don't have to bother about adding or subtracting pi. We can just say inverse tan of 1/3. So every time we refer to theta L, we're referring to this statement right here. Theta L, comma 8t sine theta L. Oops, that should be AB. The OA is simple. The OA is just the coordinate, which is 1, 3. So now we're looking at BC, which will be 4, because the magnitude of the length is 4, cosine previous angle, so theta L, plus pi over 2, since we're rotating in positive direction, 4 sine theta L plus pi over 2. And now let's look at CP. Typically the hardest, but not really if you break it down. So 4 cosine. So we're going to have 2 parentheses because we have theta L plus pi over 2. So now we're going to be looking towards in the C direction. So now we're going to want to subtract pi so that we can subtract another 2t to look at P. So minus pi minus 2t. And then same for 4 sine theta L plus pi over 2 minus pi minus 2t. And then our x of t would be equal to the sum of the components, sum of x components. And y of t would be equal to sum of y components. But that graphs the function for A, the movement of A, the motion of A. But we want to find F. So 60 degrees is 1/3 of pi, so pi over 3. So I propose that once we've rotated minus pi, we can rotate another minus pi over 3. So right here, in order to graph the model the thing for F, I'd say we can just simply minus pi over 3 minus 2t. And that would graph its movement. Hopefully that makes sense, just because it's opposite 60 degrees. And this would model path of F. So just one simple modification to get it to there. And that was our last example. Hopefully you understood this, and thank you for watching, and don't forget to subscribe for more help.